we've talked about when we have the observables for spin in the x direction, y direction, and z direction for 1 qubit. I want to talk about what happens when you have these observables for 2 qubits. S sub x, S sub y, S sub z for 2 qubits. Well, the spin for 2 qubits should be the spin for the first qubit plus the spin for the second qubit. At least it should be if the qubits are in a tensor product state. So S sub x is equal to sigma x tensor I plus I tensor sigma x, and ditto for y and z. I'm not going to write that out. And maybe I'll write this out. So sigma x tensor I is 1, 1, 1, 1, because, you take sigma x, which is just 0, 1, 1, 0, and you tensor it with I, which is identity here and identity here, plus 1, 1, 1, 1. And actually, I'm leaving out a factor of 2 because the observable was 1/2. Observable for spin was 1/2 sigma x because the spin values were spin 1/2 particles have either 1/2 pointing down or 1/2 pointing up. So that is equal to 1/2, 1, 1, 1, 1. And let's do S sub z equals 1/2 1 minus 1, 1 minus 1, plus 1/2 1, 1 minus 1 minus 1 is equal to 1, 0, 0, 1. And I guess this is I tensor sigma x, and this is sigma x tensor I. Z. Z. Thank you. Yeah?
Why isn't it sigma x tensor sigma x and sigma z tensor sigma z? What's the importance there?
Well, so we're trying to figure out what the combined spin of 2 particles is. So to get the combined spin of 2 particles, you take the first particle and take its spin, and then take the second particle and add its spin. So if we take the first part, and this is the spin of the first particle, sigma x tensor I over 2, and this is a spin of the second particle in the x direction and in the z direction. So if we multiplied them, we would be taking the spin of the first particle and multiplying it by the spin of the second particle, which would give us an observable, but it's not the observable for spin.